Right now, the most powerful storm on the surface of this planet has a destination. 170,000 Americans. No mainland connection, no highway leading anywhere safe, just 4 islands, seas building toward 30 feet, and a Category 5 typhoon that has their exact location locked in. That alone should be enough to stop the news cycle completely. But while meteorologists were processing the upgrade that changed everything about this situation, something else was registering on an entirely different set of instruments. A magnitude 5 earthquake, directly beneath the same island chain. In the same hours. 2 systems. 2 completely separate datasets. 1 shared geography. And when 2 systems like these are simultaneously active over the same ground at the same time, you are no longer dealing with a weather emergency. You are dealing with something that does not yet have a name in our planning frameworks. If what we do here matters to you, hit like and subscribe and stay with us because this story is nowhere near finished. Drop a comment and tell me where you are watching from and what time it is where you are. And I want to ask you something directly. The strongest storm on Earth is closing in on 170,000 Americans who have no way out. A magnitude 5 earthquake just registered beneath the same islands in the same window. 2 systems. 1 geography. Almost nobody connecting them. Do you think that is coincidence or something else? Tell me in the comments. Now let us get into it. The upgrade that changed everything did not arrive gradually. At 9:19 in the evening local time on April 12th, the National Weather Service office in Typhoon, Guam issued a classification that redefined the next 48 hours for every person on those islands. Super Typhoon Sinlaku had crossed into Category 5 territory. And in crossing that threshold, it became something specific and terrifying. The strongest tropical cyclone anywhere on the surface of the Earth. Not the strongest storm in the Western Pacific. Not the strongest storm of the current season. The strongest storm on the entire planet at this moment. And it is aimed directly at United States soil. The geography here is not background detail. It is the entire problem. Guam sits roughly 3,700 miles west-southwest of Hawaii. Saipan, Tinian, and Rota are positioned just to the north like a chain of stones across the Western Pacific. Together, these islands carry a combined population of approximately 170,000 American citizens. People with United States passports. People who have served in the United States military at rates that exceed most states. People who right now in this window cannot leave. There is no bridge. There is no interstate system. There is no convoy route leading away from the coast to somewhere the storm will miss. When a Category 5 typhoon locks onto your island, the options reduce to exactly 2. Find shelter where you are. Or find better shelter somewhere else on the same island. That is the complete list. The National Weather Service advisory at the moment of the upgrade was written in the precise, measured language that forecasters use when what they actually mean is that the situation has become genuinely dangerous. Tropical storm force winds already inbound. Typhoon force winds, sustained at 64 knots or greater, expected within hours. Seas building toward 30 feet. The phrase used for small craft was incredibly dangerous, which in the careful vocabulary of the Weather Service means that anything on the water is going to experience consequences that cannot be survived. Flash flooding was projected for all 4 major islands. Runoff expected across complete drainage systems, meaning that even areas sheltered from the direct wind would be dealing with water arriving from every direction simultaneously. Let me give you a comparison that might help calibrate what this actually means. Imagine a Category 5 hurricane targeting Key West, Florida. The response would be immediate, visible, and federally coordinated before the storm even reached its peak intensity. Mandatory evacuations. Contraflow on the highway system. National Guard pre-positioned. Wall-to-wall coverage on every major network. The full weight of mainland America paying attention because it would feel close and real and happening to people the cameras know how to find. 170,000 people in the Mariana Islands do not have that buffer of national attention. They are thousands of miles from the nearest television crew and thousands of miles from the nearest evacuation route. That gap between coverage and reality is not incidental. It is structural. And we are going to come back to it. But here is the thing. Here is the detail that stopped me when I was going through the data tonight. At the exact moment that upgrade was being processed, at the exact window in which the storm crossed into Category 5 territory, something else was happening beneath those islands. Something the storm advisories do not mention and the earthquake bulletins do not connect to the typhoon. When I tell you what it is, I want you to hold both things simultaneously. Because what is unfolding over those islands in the next 48 hours is not purely an atmospheric story. It is not purely a geological story. It is something sitting between the two that our planning systems were not designed to address. And that gap between what is happening and what we have prepared for is exactly where the most uncomfortable questions live. Within hours of the Category 5 upgrade, the United States Geological Survey recorded a magnitude 5.0 earthquake near Pagan Island in the northern Mariana Islands. The same chain of islands. The same arc of volcanic rock rising from the same oceanic trench. Two events, one from above and one from below, occurring over the same narrow corridor of the Western Pacific in the same narrow corridor of time. Let me be direct about what that earthquake was and what it was not, because precision here matters more than drama. Magnitude 5.0. Depth of 226 kilometers. That depth is the critical number and it matters enormously. Earthquakes at that depth do not generate tsunamis. The energy travels through too much material, dissipates over too much distance, before it can ever translate into the kind of seafloor displacement that drives a destructive wave toward a coastline. No tsunami warning was issued, and that was the correct call. We are not in a situation where a tsunami is being added to an already catastrophic forecast. Pagan Island sits approximately 300 kilometers north of Saipan. It is not currently inhabited. It sits on the same geological structure as every other island in the chain. The same string of volcanic peaks that are all surface expressions of the same enormous subduction system grinding away in the dark underneath. A magnitude 5 in the Mariana Arc on a quiet week is a data point, not a headline. Pull up the earthquake feed for this region on any given day and you will find a list. This zone moves constantly. So why does this particular event deserve a place in this video? Because of when it happened. Two timelines activating simultaneously. One above the islands, one below them. And the question that researchers in compound hazard analysis would ask, and I want to be transparent that I am raising this question rather than answering it, is whether two simultaneous extremes can produce outcomes that neither would produce independently. Think about what this looks like from the ground level on Saipan right now. The sky is tightening. Barometric pressure is dropping in ways you can feel in your ears before you ever look at a gauge. The surf is building. Emergency alerts are lighting up phones. People are doing what people do before a catastrophic typhoon arrives. Taping windows, moving furniture away from glass, filling every available container with water, trying to remember where they put the flashlights. And somewhere beneath their feet, 226 kilometers down in the geological zone where the Pacific plate grinds against the mantle below, the Earth released stress tonight. The ground under those islands moved. That was a real event. It registered on real instruments. Most of the time, a deep slab earthquake in the Mariana Arc is a footnote that goes straight into a database and never becomes a headline. Nobody writes about it because on its own, there is nothing unusual to say. But we are not in a normal situation tonight. Because the ground that earthquake occurred beneath is about to be loaded from above by the strongest storm on Earth. And those two facts sitting next to each other create a question that existing emergency planning frameworks have not been designed to answer. Not whether the earthquake will make the typhoon stronger. The physics do not connect in that direction. The question is what happens to saturated soil, to destabilized slopes, to infrastructure that has already been stress tested by Category 5 winds, when you also add seismic loading to the same geography in the same window. What happens when the loading comes from above and below simultaneously? And the honest answer, as best we can determine it right now, is that we do not fully know. That uncertainty, hanging over 170,000 people who cannot leave, is the thing that should be keeping every emergency planner awake tonight. Let me state the core claim of this video plainly because The rate of change crossed what meteorologists define as rapid intensification, a wind speed increase of at least 30 knots within a 24-hour period, not once but multiple times. This was not a storm that slowly built strength over a predictable timeline. This was a storm that accelerated in ways that compressed the warning window available to the people in its path. That compression matters in a specific and terrible way for 170,000 people who cannot evacuate. On the mainland, when a storm rapidly intensifies from Category 3 to Category 5, the response is to move faster, accelerate mandatory evacuations, push resources forward. The infrastructure of escape, the highways and airports and fuel depots, is still available even if the window is shrinking. In the Marianas, there is no infrastructure of escape. The window closing faster does not change the available options. It changes only the amount of time people have to prepare in the one place they are going to be when the storm arrives. Consider what the people on these islands already know from experience. Typhoon Pangsona struck Guam in December of 2002 with sustained winds of 150 miles per hour. Recovery took years. Typhoon Mawar struck in May of 2023 and left an estimated $3.3 billion in damage. Mawar made landfall while weakening from its peak. Sinlaku is approaching at or near its peak intensity. And it is doing so in April, when the seasonal muscle memory of typhoon preparedness is not yet fully activated, when institutional readiness is calibrated to a different part of the calendar, when the public's psychological alertness that comes with the heart of typhoon season has not yet been triggered. Now add the geological layer. Take the April anomaly. Add the rapid intensification that crossed the threshold multiple times. Add the Category 5 ceiling. And then add a magnitude 5.0 earthquake on the same volcanic island arc in the same time window. Each of those elements has occurred before in isolation. Deep Mariana earthquakes happen regularly. Off-season Western Pacific typhoons occur occasionally. Category 5 landfalls happen somewhere in the basin every few years. But the specific combination of all four simultaneously, Category 5, April, the CNMI in Guam in the direct path, no evacuation capacity, seismically active subduction zone registering events in the same window, does not have a clean historical analog. We are not drawing on a library of previous events to understand what comes next. We are in comparatively uncharted territory. Picture a loose cluster of thunderstorms spiraling over warm water. Unremarkable. The kind of system that forecasters flag and monitor but do not yet worry about. 4 days ago, that was roughly what Sinlaku was. A system with potential, sitting over a part of the Pacific where the water was warm and the atmospheric setup was cooperative. Then the transformation began. Day 1 it organized. The low-pressure center tightened. The towering thunderstorms that formed the engine of tropical cyclones began wrapping more symmetrically around that center. Day 2 it crossed into tropical storm classification. Sustained winds at 39 miles per hour and a clearly defined circulation. Day 3 is where the remarkable part begins. The structure shifted into rapid intensification. The eye began to contract. As the eye contracts, the rotation around it accelerates, exactly the way a figure skater pulling their arms inward spins faster. The surrounding eye wall tightened. Central pressure dropped quickly. 30 knots of wind speed added in 24 hours. Then another 30. The rapid intensification threshold crossed once, then crossed again. By day 4, a Category 5 system with an eye clearly visible on satellite, a storm that if you watched its radar loop would look almost geometric in its terrible symmetry. Here is why that pace matters for people who have nowhere to go. Warning systems and public communication are calibrated to the historical rhythm of storm intensification. When a storm follows a gradual path from tropical storm to major typhoon, authorities have time to escalate their messaging in steps that people can process and act on. When a storm keeps outrunning its own forecast models, that calibration breaks down. The public may still be operating on yesterday's advisory while today's reality has fundamentally changed. Research on previous rapid intensification events consistently found this pattern. Even when the technical forecasting is accurate, the public response lags. And Sinlaku by any measure intensified faster than anything the Marianas have experienced in recent institutional memory. There is a reason this storm reached Category 5 in April. The fuel source is not random. It is sitting in the ocean and it connects this storm directly back to the same islands, the same geology, and the same moment in time we began with. The water that powered Sinlaku floats above the deepest trench on this planet. That is not a coincidence. That is geography. And tonight, geography is fate. The surface temperature of the ocean is what most people think of when they think about tropical cyclone fuel. Warm water evaporates, moisture rises, the atmospheric engine runs. That is correct as far as it goes. But it is incomplete in a way that turns out to matter enormously for understanding why Sinlaku reached Category 5 in April. The fuller picture is ocean heat content. Not just how warm the surface is, but how warm the water is from the surface down through the upper layers of the ocean. When a tropical cyclone passes over the ocean, its churning stirs up the water column. If the warm layer is shallow, this stirring brings cooler water to the surface and effectively starves the storm. That is one of the primary self-limiting mechanisms of tropical cyclones. The storm weakens its own fuel supply as it moves. But when the warm layer is thick, when the heat extends well below the surface, that self-limiting mechanism is suppressed. The storm churns, the warm water at depth replenishes the surface, and the fuel supply remains essentially uninterrupted. The storm finds no reason to stop intensifying because the ocean refuses to cool. The Western Pacific Warm Pool is one of the most thermally energetic bodies of water on Earth. It sits broadly in the region bounded by the Philippines. Indonesia existed a generation ago. The current Pacific transition from El Niño toward neutral conditions means that subsurface heat which accumulated during the El Niño phase is still present in the water column. A Kelvin wave, a pulse of warm water traveling beneath the surface, has been propagating through this region. Surface temperatures warm. Subsurface temperatures warm. The thermal structure of the water underneath Sinlaku gave the storm no reason to weaken and every reason to accelerate. And this is the direct geographical link back to tonight's compound scenario. The ocean that handed Sinlaku its Category 5 status sits above the Mariana Trench. The heat that allowed this storm to become the strongest on Earth before making landfall on United States territory floats above the same subduction zone that moved tonight. I'm not suggesting those two facts are causally connected. They are not in any direct physical sense. But they are geographically inseparable. And that geography means both the atmospheric extreme and the geological activity are centered on the same piece of the planet. That piece of the planet has 170,000 people on it. There is another variable in storm behavior that receives less attention than it deserves, and that matters significantly for the Mariana scenario. Sinlaku has maintained its forward motion. It has not stalled, has not wandered, has not meandered over open water the way some Western Pacific typhoons do. This matters because a stalling storm eventually exhausts its own fuel supply, churning the same water until that patch of ocean has given up most of its heat. Stalling is one of the mechanisms by which powerful storms weaken before they arrive at a coastline. The atmospheric steering pattern guiding Sinlaku has been consistent throughout its intensification. A subtropical ridge to the north channeling the storm along a northwest track with sustained forward velocity. No significant wind shear events. No blocking patterns forcing a loop or slowdown. The storm moved efficiently, maintained its structure, and continued intensifying. In the technical language of tropical meteorology, it is a well-organized system operating in a favorable environment. A polite way of saying the atmosphere provided everything the storm needed and stayed out of its way. What this means practically is that the islands are not receiving a storm that has had time to partially exhaust itself over open water. They are receiving the full uninterrupted output of a system that the ocean fed continuously and that the atmosphere steered directly toward them. The energy that the Western Pacific has been storing in that water column is going to arrive concentrated and intact over inhabited United States territory. Which brings us back to the ground. Because ground that is about to receive the concentrated energy of a Category 5 typhoon, the rainfall, the surge, the sustained wind loading, is not the same ground that received a normal week of weather. Whether or not the seismic activity registered tonight becomes a direct complicating factor, the physical state of the soil and slopes on those islands after Sinlaku passes will be fundamentally different from what it was before. That matters. And it matters more in this specific geography than almost anywhere else on Earth. In an average April, the Western Pacific produces roughly 0.7 named tropical storms total. That figure covers all intensity levels. Everything combined. The statistical expectation for April in this basin is less than one storm of any kind. Not zero but close. And yet, Category 5 April, direct track toward Guam and the Commonwealth of the Northern Mariana Islands. Whether this represents a genuine shift in the climatological baseline or a low-probability event that simply happened to materialize is a scientifically open question. Researchers are careful about attributing individual events to long-term trends, and that caution is appropriate. A single April Category 5 does not prove that April Category 5s are becoming common. But it does demonstrate that the conditions required to produce one are present in this basin in this season right now. Which means the historical assumption that such events are restricted to peak season is no longer as reliable as it once was. And here is where the timing thread matters most for tonight's compound scenario. The fact that this storm is occurring in April rather than August is not a meteorological footnote. April is precisely the timing that placed this storm's peak intensity over the same island chain where seismic activity registered tonight. The specific alignment of this storm, this trajectory, this week, this geological moment is what brought both systems to bear simultaneously over the same people. To understand why that alignment matters as much as it does, you need to go somewhere that storm coverage almost never goes. 226 kilometers straight down. Before we can talk about what tonight's earthquake means, we need to talk about what produced it. And to do that properly, we need to visit the most extreme geological environment on this planet, sitting directly beneath the islands at the center of this entire story. The Mariana Trench is the deepest structure on the surface of the Earth. Challenger Deep, the lowest known point, descends approximately 10,935 meters below sea level. To make that number processable, if you placed Mount Everest at the bottom of the Mariana Trench, its summit would still be more than a mile underwater. This is not just the deepest point in the ocean. It is the deepest point anywhere on the planet that human instruments have reached and measured. The trench exists because of subduction. The Pacific Plate, one of the largest tectonic plates on Earth, carrying some of the oldest oceanic crust on the planet, roughly 150 to 170 million years old, is converging with the Philippine Sea Plate. The Pacific Plate is older, denser, and colder. When two oceanic plates converge and one is denser, the denser one descends. It bends downward and begins its journey into the mantle. The trench is the surface scar of where that bend happens, where the Pacific Plate tips over the edge and begins its long descent. The convergence rate is approximately 4 to 7 centimeters per year. Slow in human terms. Sufficient over millions of years to produce the deepest trench on Earth. The volcanic islands of the Mariana Chain, Guam, Rota, Tinian, Saipan, Pagan, Agrihan, are not sitting on stable passive crust. They are sitting on an island arc, a chain of volcanoes formed where the descending Pacific Plate reaches depths where it releases water into the overlying mantle material, lowering the melting point, generating magma that rises toward the surface. The islands are built from the subduction process. They are the above-water tips of a volcanic system whose roots connect directly to the grinding interface between two of the largest tectonic plates on Earth. What this means for tonight's compound scenario is geographically fundamental. The islands do not merely sit near the seismic system. They are part of it. When we talk about a magnitude 5 earthquake near Pagan Island, we are talking about an event that occurred within the same geological structure that includes the rock and soil under every house, hospital, and emergency shelter on Guam and Saipan. The Pacific Plate material subducting under the Marianas is some of the oldest oceanic crust on the planet. Old oceanic crust is cold oceanic crust. Cold rock is brittle rock. And brittle rock subjected to the extraordinary pressures of subduction does not bend and flow the way warmer, younger material would. It breaks. It fractures. The descending slab carries its brittleness with it as it sinks, which is part of why the Mariana system produces earthquakes at depths that most other subduction zones do not. The slab retains its mechanical integrity well below the depths where other plates would have deformed. 226 kilometers of depth is within what seismologists call the Wadati-Benioff zone, the plane of earthquake activity that traces the descending slab as it subducts. This is exactly where tonight's earthquake was generated. Inside the cold, brittle slab of Pacific crust in the zone where accumulated stress produces ruptures that send waves upward through hundreds of kilometers of rock toward the surface above. The islands are above. The slab is below. The trench is between them. And right now, a Category 5 typhoon is bearing down from above while the slab beneath registers activity in the dark. Here is something that most reporting on deep earthquakes gets wrong by implication. When a shallow earthquake occurs at 10 or 15 kilometers of depth, the energy release is close to the surface. Ground shaking is intense. If the rupture occurs underwater, tsunami generation is an immediate concern. Shallow earthquakes near coastlines are the ones that kill people directly and trigger warning systems. When journalists and emergency managers think about earthquake risk, they are mostly thinking about shallow events. Deep earthquakes are different in ways that matter enormously. An event at 226 kilometers is occurring roughly 140 miles underground. The seismic waves that reach the surface have traveled through enormous amounts of material, and that material absorbs and disperses the energy along the way. Surface shaking for a given magnitude is far less intense than it would be for a shallow event. A magnitude 5 at 226 kilometers produces far less violent surface motion than a magnitude 5 at 10 kilometers. This is why deep slab earthquakes, even in populated regions, are often barely felt at the surface despite being clearly detected by sensitive instruments. No tsunami was generated tonight, and that is correct. It is settled physics. So in one sense, tonight's earthquake is properly classified as a non-event in isolation. And yet the deeper story is about what a deep slab earthquake tells us about the state of the system producing it. The Wadati Benioff zone is not a random scattering of stress. It is a structured plane of seismicity tracing the descending slab. Earthquakes within it occur because the slab is under stress. The forces of subduction load it from one direction while the resistance of surrounding mantle material pushes back from another. The brittleness of the old Pacific crust means stress accumulates in the slab rather than being released gradually through slow deformation. Tonight's magnitude 5 is a relatively modest release on the scale of what this system is capable of. The magnitude scale is logarithmic. Each unit represents approximately 32 times more energy than the one below it. A magnitude 5 and a magnitude 6 are not close. They are 32 times apart in energy release. But here is the question that compound hazard researchers find worth asking. Does a seismic event in the Wadati Benioff zone, even a modest one, tell us anything about the stress state of shallower portions of the same system? Can energy redistribution at depth influence the likelihood of activity closer to the surface? This is not settled science. There is active research on what seismologists call stress transfer, the idea that a rupture in one part of a fault system can change the stress balance in adjacent portions. I am not telling you tonight's earthquake is a precursor. I am not telling you the system is about to produce a shallower, larger event. I genuinely do not know, and anyone telling you they do know is operating beyond what the current data supports. What I am telling you is that the ground above that 226-kilometer earthquake is about to be loaded from above in the most extreme way the atmosphere knows how to load it. 30-foot seas against coastlines. Rainfall measured in inches per hour across volcanic island slopes. Wind loading on structures that were not all built to current standards. And that loading belongs in the same conversation as the geological activity below. 300 kilometers north of Saipan, Pagan Island rises from the Pacific as two connected volcanic structures separated by a low saddle. Together they form what geologists classify as a stratovolcano complex, steep-sided, built from alternating layers of lava, ash, and pyroclastic material. The kind of volcanic architecture that produces dramatic topography and under certain conditions dramatic instability. Pagan's most recent modern community was evacuated in 1981 following a major eruption that buried the island in ash and made habitation impossible for years. The most recent significant eruptive activity was in 2012. The volcanic system beneath Pagan is not dormant. It is quiet. There is a meaningful difference between those two words. That distinction matters for how we think about slope stability. Volcanic islands built from repeated eruptions have a material composition that makes them behave differently under stress than islands built from older, more consolidated rock. The slopes of stratovolcanoes like Pagan include loose pyroclastic material, hydrothermally altered rock chemically weakened by interaction with volcanic fluids, and unconsolidated ash deposits. These materials do not have the same cohesive strength as solid basalt or granite. They are susceptible to what geologists call flank instability, the tendency for portions of a volcanic slope to fail, particularly under external loading like heavy rainfall or ground shaking. The underwater flanks of these volcanic islands, the portions of the structure extending below sea level, are often steeper and composed of the same vulnerable material. Submarine landslides on volcanic island flanks are not theoretical events. The Canary Islands have a well-documented history of large-scale flank collapses. Hawaii's geological record includes signatures of enormous prehistoric submarine landslides. The mechanism for triggering these events includes both seismic loading and rapid saturation of volcanic material. Ground shaking reduces the shear strength of slope materials, particularly those that are already wet. Rapid rainfall, the kind a Category 5 typhoon delivers, saturates slopes and raises the groundwater table, further reducing the effective friction holding materials in place. When both processes occur in the same time window, the stability threshold for a given slope is reached at a lower level of combined stress than either process alone would require. I want to be careful about scale here. Tonight's magnitude 5 at 226 kilometers is below the threshold seismologists typically associate with spontaneous triggering of major submarine landslides. The commonly cited threshold for earthquake-triggered submarine collapses is in the magnitude 6.5 to 7 range, with shallower events being more effective triggers than deeper ones. Tonight's event is smaller and deeper than that typical trigger profile. We are not in a situation where a major slope collapse is an immediate and likely outcome of tonight's seismicity alone. But we are in a situation where a volcanic island with inherently unstable slope material is going to receive Category 5 typhoon conditions in the same general time window as seismic activity in its immediate vicinity. And the question of how those two processes interact, even if neither alone would trigger failure, is not one that existing emergency management frameworks are designed to address systematically. Here is the question this entire video has been building toward. I want to be transparent about exactly what the data supports and what it does not. Tonight's magnitude 5 earthquake at depth does not tell us by itself that the Mariana seismic system is in an elevated state above its historical baseline. It is consistent with the normal background seismicity of a highly active subduction zone. On any given week in the Mariana Arc, you might see several events at this magnitude. So in one honest reading, the answer to whether this earthquake tells us something alarming is, not definitively. But here is the concept that deserves careful attention. In seismically active regions, earthquakes do not always occur in perfect isolation from each other. There are periods of elevated activity, windows in which a zone produces more events than its baseline rate would predict. Identifying a cluster versus a background fluctuation in real time is genuinely difficult. The difference often only becomes clear in retrospect. This is one of the fundamental frustrations of operational seismology. The signals that matter most are often the hardest to read in the moment they are occurring. The Mariana system is registering activity right now. Whether tonight's event is part of an elevated cluster or simply a point on a normal background distribution is something that scientists monitoring the zone are better positioned to assess than I am. What I can say is that the timing, an event occurring in the hours around the Category 5 upgrade of a storm heading directly for the arc, creates a compound context that does not exist when any single event in this zone is reported in isolation. Now connect this to the physical question the typhoon raises. The storm is going to deposit extraordinary amounts of water on those islands. Not unusual amounts for a typhoon. Category 5 amounts. Rainfall rates that can reach several inches per hour. Total accumulations measured in feet. That water is going to saturate the soil. It is going to raise groundwater tables. It is going to change the effective weight pressing on slopes. It is going to flow into subsurface cracks and pore spaces that in their normal state provide friction and cohesion. Geotechnical engineers call this pore pressure increase. When water saturates soil and rock, the water pressure in the pore spaces pushes outward against the friction holding the material together. High enough pore pressure and friction drops. Slope materials that were stable in dry conditions become unstable. This is the mechanism behind most rainfall-triggered landslides, one of the most consistent secondary hazards associated with major tropical cyclones worldwide. Now introduce the seismic dimension. Even at modest magnitude and significant depth, a seismic event produces ground motion that can affect the structure of slope materials, particularly those already close to their stability threshold. In geotechnical terms, seismic shaking can induce liquefaction in saturated granular materials, reducing their effective strength. It can also act as a trigger for slopes that rainfall saturation has brought to the edge of failure, the final increment of stress that pushes them over. The scenario I am describing does not require a major shallow earthquake. It requires only that the seismic background activity of the Mariana system remains non-zero during the window when the typhoon is depositing maximum water on slopes that are geologically susceptible. That window is open right now. Let me start with a definition because precision matters here more than anywhere else in this video. A compound hazard in the technical language of disaster risk research is a situation in which two or more hazardous events occur simultaneously or in close succession and interact in a way that amplifies the overall risk beyond what either event would produce independently. The key word is interact. It is not simply that two bad things happen at the same time. It is that their interaction through shared physical processes, shared infrastructure, or shared response resources produces outcomes that adding the two events independently would not predict. Single hazard frameworks are the dominant model in emergency management. A typhoon emergency operations plan optimizes the response to a typhoon. A seismic preparedness plan optimizes the response to an earthquake. Personnel, resource flows, decision trees, communication protocols, all structured around one primary event with defined characteristics. When the primary event is a Category 5 typhoon, the framework activates typhoon response. When it is an earthquake, the framework activates seismic response. There is no established compound response framework for Category 5 typhoon plus active subduction zone seismicity occurring simultaneously. That is not a criticism of emergency management professionals. They are working with the planning tools that exist, built on the historical record of events that have actually occurred and been studied. The historical record simply has very little data on this specific combination over the specific geography of the Marianas. What does that gap look like in practice? Consider what I would call the synchronization problem. When a typhoon is active, emergency responders are sheltered in hardened facilities. They are not moving because moving in a Category 5 typhoon is how responders become victims. Response capability is essentially frozen during the height of the storm. If during that frozen window a seismic event of sufficient magnitude and proximity were to occur, the response to that secondary event would have to wait until the primary event permitted operations to resume. Two events. Sequential response. And the sequence matters enormously when lives depend on timing. System fragility is the other concept worth naming. Engineered systems, buildings, bridges, power networks, water treatment facilities, are designed with safety margins that account for the expected range of loading over their operational lives. A building designed to Category 4 wind loading might have a margin extending to weak Category 5 conditions. That same building might also have a seismic design accommodating a moderate earthquake. But those margins are evaluated independently. The question of whether a building that has absorbed Category 5 wind damage still retains its designed seismic resistance capacity has not been systematically addressed in most building codes because the joint probability of experiencing both and a Category 5 typhoon does not deliver rainfall in gradual absorbable increments. It delivers it as a sustained assault at rates that exceed the capacity of the ground to drain, the rivers to carry, and the engineered drainage systems to handle. The first stage is familiar. Surface flooding. Runoff from intense rainfall collects in low areas, blocks roads, enters buildings. Emergency managers plan for this. The second stage is less visible and more consequential. As rainfall continues, water that does not run off infiltrates into the soil. Pore spaces fill. The groundwater table rises. In volcanic island terrain, which describes the Marianas, the soil overlying volcanic rock includes materials with relatively low permeability in clay-rich horizons and higher permeability in fractured volcanic zones. Water moves through these systems unevenly, creating localized zones of saturation that can develop faster than surface monitoring would indicate. When a slope reaches full saturation, its behavior changes fundamentally. In dry soil, friction between particles and the cohesion of clay minerals hold the slope together. As water fills the pore spaces, it exerts pressure that pushes particles apart and reduces effective friction. The same principle that makes dry sand stable at a steep angle and wet sand flow applies to volcanic soil and weathered rock on typhoon-soaked island terrain, just at a scale that can involve entire hillsides. Slope failures will occur during Sinlaku. The question is not whether landslides will happen. They will. The question is where, how large, and whether their consequences are amplified by concurrent seismic activity. Coastal erosion is the other process worth naming. 30-foot seas driven by a Category 5 typhoon exert enormous force on coastlines. The bases of coastal cliffs, the faces of seawalls, the foundations of structures near shorelines all receive impacts that undermine structural integrity. When surge carries sediment away from the base of a cliff, It removes the support holding the upper portion in place. Coastal failures driven by undercutting at the base are documented consequences of major typhoon events. The submarine coastal slopes face risk as well. The seafloor drops steeply away from the volcanic Marianas. These are not gently sloping continental shelf environments. Material destabilized and sliding off an island submarine flank moves fast. And moving underwater material displaces water. Let me describe a sequence, not a prediction. A sequence of physical events, each grounded in documented geological process, that could unfold when the conditions we have been discussing converge in the same place at the same time. A volcanic island composed of alternating layers of lava, pyroclastic deposits, and hydrothermally altered rock has been accumulating material on steep submarine flanks for thousands of years. Those flanks extend from the shoreline down to great depths at angles that in some cases approach or exceed the angle of repose, the steepest angle at which a given material remains stable. The only reason these slopes maintain their structure is the mechanical strength of competent volcanic rock layers acting as scaffolding holding the weaker material in place. A major typhoon arrives. Rainfall saturates the exposed land surface and infiltrates the volcanic edifice. Groundwater tables rise within the volcanic rock, increasing pore pressure throughout the structure, including within the submarine flanks below the waterline where hydrological connectivity allows storm-driven pressure increases to propagate offshore. Simultaneously, 30-foot seas pound the base of the island's coastal cliffs, removing material that was providing lateral support. And the seismic system registers activity. Even at depth and modest magnitude, seismic waves add dynamic stress to slopes already close to their stability threshold. The frequency content of the waves may be sufficient to push a near-critical slope over the edge. Somewhere on a submarine flank, a slope that has been loaded by all three processes simultaneously reaches the point where friction can no longer hold. A section mobilizes. It moves downslope. The mass of that material displaces water as it goes. Water displaced by a submarine mass movement does not simply absorb the energy. It transmits it. The displacement generates a wave. This is the mechanism behind what researchers call displacement waves, and they are distinct from seismically generated tsunamis in important ways. Traditional seismic tsunamis are generated by the vertical displacement of large seafloor areas along a megathrust fault. They are detected by the global buoy network. They propagate over long distances. Warning systems are specifically designed for them. Displacement waves from submarine landslides are more localized, more variable in direction, and potentially faster to arrive at nearby shorelines because the source is close. In some documented historical cases, the wave arrived at a nearby shoreline before any warning system could activate. I want to be responsible about the threshold question. Triggering a submarine landslide large enough to generate a meaningful displacement wave typically requires either a very large seismic event or a preconditioned slope already near critical instability. Tonight's magnitude 5 at 226 kilometers is below the typical trigger profile. The vast majority of submarine slopes in the Marianas are not critically unstable under normal conditions. What the compound scenario does is change the definition of normal. A slope requiring a larger seismic trigger to mobilize under dry, unloaded conditions may require something smaller if it is simultaneously saturated by a Category 5 typhoon and loaded by ground motion from even a moderate event. The threshold shifts downward. By how much depends on the specific material properties of each slope, the degree of pre-existing saturation, the depth of the water table, and variables that cannot be assessed in real time from the outside. This is the scenario. Not certain. Not imminent. A threshold that is lower tonight than it was last week over the same islands, above the same 170,000 people. Guam's infrastructure is not a mystery. After Typhoon Mawar in 2023, there was substantial documentation of what a major typhoon does to the island's engineered systems. $3.3 billion in damage. Power outages affecting nearly the entire island, some lasting months. Water system failures as treatment plants lost power and pressure. Road closures from landslides, flooding, and structural collapse. A port struggling to handle the surge in incoming recovery supplies while simultaneously managing damage to its own facilities. A recovery timeline measured in months even with significant federal support. And that was from a powerful but not Category 5 typhoon. Sinlaku is approaching as Category 5. The power grid is the critical single point of failure from which almost every downstream consequence flows. When it goes down, and it will go down because no grid is engineered to survive Category 5 wind loading without significant damage, the consequences cascade immediately. Hospitals fall back on generator power. Generators carry fuel reserves measured in hours to days, not weeks. Water pumping stations stop. Wastewater treatment stops. Refrigerated medications and food supplies begin to warm. Air conditioning in a tropical climate is not a comfort issue. It is a medical issue for vulnerable populations who cannot thermoregulate without it. Guam's hospital capacity is limited relative to the population it serves. In a compound event where both typhoon injuries and geological event injuries would be presenting simultaneously, capacity becomes acute. Emergency medical care is a resource that gets consumed quickly when demand spikes, and it cannot be resupplied from the mainland in hours. The aircraft that might bring additional medical resources cannot fly through a Category 5 typhoon. They are waiting on the ground thousands of miles away. Supply chain isolation is the structural vulnerability in any major Mariana disaster scenario, and it does not receive adequate attention in mainland coverage. The Marianas are not connected to the global supply chain the way mainland ports are. Container ships arrive on schedules calibrated to normal demand. Fuel is held in limited on-island storage. Building materials must be ordered and shipped from thousands of miles away. After Mawar, some residents waited months for construction materials. Not because of bureaucratic failure, but because the physical logistics of supplying an island in the middle of the Western Pacific are genuinely difficult. Distance is not a policy problem. Distance is a physics problem. A Category 5 typhoon followed by any additional geological event, even one well below catastrophic thresholds, would extend that recovery timeline. Every additional element of damage adds to the volume of materials needed. Every additional element of infrastructure failure adds to the list of systems requiring repair before the community can function normally. The compounding is not linear. It is not Mawar plus a little more. It is potentially Mawar multiplied by a factor whose value depends on variables that are right now unresolved. There is a question that makes most geologists uncomfortable when it is asked directly. Can an atmospheric event, a tropical cyclone, actually influence seismic activity? The conventional answer, delivered with appropriate scientific caution, is almost certainly not in any meaningful way for events of this scale. Earthquakes are driven by the accumulation and release of tectonic stress over years to decades. A typhoon lasts days. The energy scales are vastly different. But that is not quite the end of the story. There is a hypothesis studied in the peer-reviewed scientific literature that relates to what happens to the crust when a large tropical cyclone passes over it. The atmospheric pressure at the center of a major typhoon drops to extraordinarily low values. That drop in atmospheric load is, in a real physical sense, a reduction in the weight pressing down on the crust beneath the storm. The hypothesis is that fault systems already near their failure stress threshold might be very slightly influenced by this change in surface loading. Researchers have published work examining correlations between typhoon passage and slow earthquake events, periods of subtle fault movement detected by sensitive GPS instruments. The correlations found were small. The mechanism proposed was tenuous. The scientific community received it with appropriate caution. This is not established consensus. It is a finding that has been noted, examined, and not yet convincingly replicated in a way that would move it from interesting to operational. What it represents in the context of tonight's situation is not a confirmed mechanism. It is an example of how the boundary between atmospheric and geological systems may be less impermeable than our models assume. If fault systems near failure threshold can be influenced even very slightly by the surface loading changes associated with a Category 5 typhoon passing directly over them, then the separation we maintain in our models between storm risk and earthquake risk may be overstated. I want to be precise. I am not claiming the typhoon triggered tonight's earthquake. The timing does not establish causation, and the physics are not convincingly established in the literature. What I am claiming is that the question of atmospheric geological coupling deserves more attention than it currently receives. And that attention is most urgently needed when, as is the case tonight, both systems are simultaneously peaked over the same inhabited geography. Guam is not simply a civilian population center. It hosts Andersen Air Force Base and Naval Base Guam, two of the most strategically significant military installations in the Western Pacific. Anderson hosts bomber and surveillance assets. The naval base supports submarine and surface operations across the Indo-Pacific. In the context of current regional geopolitical dynamics, these installations are not incidental. They are central. The military operates under its own tropical cyclone condition of readiness system which stages preparation levels in advance of major storms. Military facilities have hardened infrastructure, pre-positioned resources, and response capabilities that exceed what is available to the civilian population. After war, military assets were central to the early response and recovery on Guam. The question that deserves acknowledgement without overclaiming is this: how much of what happens to military readiness under a compound event, a Category 5 typhoon coinciding with geological instability, is transparent to the civilian population sharing the same islands? The military does not publicize its operational status. That is appropriate for operational security reasons. But it creates an information asymmetry at exactly the moment when the civilian population most needs confidence about the full picture of available response capacity. This is not an accusation. It is an observation about the structure of information flow during compound events over territory that is simultaneously civilian and military. Even the best hardened infrastructure has limits, and those limits during this event are being tested in ways that no test scenario likely anticipated. The residents of Guam, Saipan, Tinian, and Rota are American citizens. They serve in the United States military at rates that exceed those of most states. A remarkable level of service commitment from a population that in return receives limited representation in the federal government. They cannot vote for president. They have a non-voting delegate in the House. They have no representation in the Senate. When federal decisions are made about disaster preparedness funding, infrastructure investment, or the speed and scale of post-disaster response, the political weight of 170,000 territorial residents is structurally lower than the political weight of the same number of people in a state. Typhoon Mawar in 2023 generated significant criticism of federal response speed and scale relative to what would have been deployed for an equivalent event on the mainland. $3.3 billion in damage. Months without power for large portions of the island. Recovery still incomplete in some areas more than a year later. The argument that territorial residents receive less than they would if they were in a state is not a fringe grievance. It is a documented pattern. And when compound hazard reduces the margin for error in emergency response, the consequences of that structural gap are not abstract. They are measured in recovery time and in the slow erosion of resilience in communities that have already been told in practice, if not in policy, that they are second in line. 170,000 people. The strongest storm on Earth. A seismically active subduction zone. And a political structure that does not give them the representation needed to change any of this through the normal mechanisms of democratic pressure. That is the human layer of the compound hazard, and it belongs in the same conversation as the atmospheric and geological ones. I need to address something directly because if you have spent any time reading about the Mariana Trench and earthquakes online, you have almost certainly encountered it. The idea that the Mariana system is quietly building toward a mega-thrust event, an enormous civilization-disrupting earthquake along the subduction zone, has significant presence in certain corners of internet geology coverage. I want to talk about it honestly because the way it usually gets discussed is either so catastrophist that it becomes useless or so dismissively debunked that it leaves out things genuinely worth knowing. Let me separate the fear from the science carefully. First, the part that is real. The Mariana subduction zone is in principle capable of producing very large earthquakes. That is not speculation. That is basic plate tectonics. The mechanics of subduction, one plate diving beneath another, stress accumulating over decades and centuries at the locked interface between them, can generate megathrust events. The historical record of the Pacific Rim includes evidence of events well above magnitude 8. The Tohoku earthquake off Japan in 2011 reached magnitude 9.0 and generated the tsunami that caused the Fukushima nuclear disaster. The Valdivia earthquake in Chile in 1960, the largest instrumentally recorded earthquake in history, was magnitude 9.5. These are real events produced by real subduction systems. The architecture exists in every subduction zone on the planet. Here is where the internet version of this story goes off the rails. The question is not whether a subduction zone exists. The question is what kind of subduction zone it is, because not all subduction zones behave the same way. The Pacific Plate subducting under the Philippine Sea Plate in the Mariana System is old, cold, and dense. When that cold, dense slab reaches the subduction zone, it plunges steeply at an angle far more extreme than the Cascadia System or the Chilean subduction zone. This steep geometry has a specific consequence for what seismologists call plate coupling. Plate coupling is the degree to which the two plates are mechanically locked together at their interface. High coupling means the plates are effectively stuck to each other, building up stress that releases catastrophically when the lock breaks. That is how you get a magnitude 9. Low coupling means the plates are sliding past each other more freely, accumulating less stress at the interface and releasing it in smaller, more frequent events rather than one enormous rupture. What the scientific literature suggests, and I want to be precise because this remains an active area of research without a definitive consensus, is that the specific geometry of the Mariana System with its old cold steeply subducting slab may produce relatively low coupling between the plates. Some researchers have argued this lowers the maximum magnitude of potential megathrust events in this system compared to the better-known catastrophic subduction zones elsewhere in the Pacific. I want to be very careful about what I am and am not saying. This does not mean the Mariana System is safe. It does not mean a large earthquake is impossible. What it means is that the question of maximum possible event size is considerably more nuanced than either catastrophic speculation or breezy reassurance would suggest. Tonight's magnitude 5 deep slab event does not tell us anything about where the megathrust stress state stands. The deep slab earthquake occurred within the subducting Pacific Plate itself. The megathrust interface, where a catastrophic rupture would originate, is a different structure at a different geometry and a different depth range. These are not the same fault system. An event within the slab does not necessarily tell us about the state of the interface above it. Tonight's earthquake is not a megathrust warning. I want to be unambiguous about that. But the fear, the widespread persistent sense that something enormous is possible in this system, is not irrational. It is a response to real geological complexity that has been inadequately communicated to the public. The failure is not in the people feeling uneasy. The failure is in the gap between what the science actually says and what gets communicated publicly about this system. In the 7 days prior to tonight's events, the United States Geological Survey recorded approximately 87 earthquakes globally at magnitude 4.5 or greater. 87 in 1 week. More than 12 significant seismic events every single day somewhere on this planet. Japan registered multiple events. Indonesia saw activity along its volcanic arc. Alaska produced several moderate quakes along the Aleutian chain. The Ring of Fire was doing what the Ring of Fire always does. Moving, grinding, releasing stress in the incremental, relentless way that a geological system at the boundary of converging tectonic plates has been doing for tens of millions of years. The Earth was being entirely, completely, unremarkably itself. One of the ways that online coverage of geological events misleads people is by presenting individual earthquakes as if they are occurring against a backdrop of normal silence. As if the Earth is usually still and these events represent departures from quiet. It is not still. It has never been still. The baseline is not silence. The baseline is 87 magnitude 4.5 or greater earthquakes per week, every week, year after year, whether or not anyone is watching. Most of it never reaches you because most of it should not reach you. A magnitude 4.8 at 500 kilometers depth in a remote stretch of the Western Pacific is not news. It is geology. It belongs in a database, not a headline. So let me be precise about why tonight's Mariana Arc event belongs in this video. The Mariana Arc is not uniquely active right now relative to other parts of the global seismic system. Let me say that again clearly. The Mariana Arc is active in the same way it is almost always active, consistent with its role as one of the most geologically dynamic zones on Earth. Yes, but not elevated above its own historical baseline in any dramatic way based on tonight's single event. The background seismic activity of the Pacific is always loud. That is not a reason for complacency. It is a reason for calibration. The kind of careful, precise calibration that identifies same inhabited geography in the same hours. Think of it this way. The background seismic activity of the Pacific is like the background noise of a city. Traffic, construction, the general hum of millions of people and machines. You tune it out because if you treated every noise as a signal, you would never be able to function. The noise is real, but it is not information. Now imagine that same background noise on the night a Category 5 hurricane is making landfall on those same streets. Suddenly the background is no longer irrelevant. That construction equipment is now a flooding risk if it blocks a drainage channel. The background has not changed. The context around it has changed everything about what the background means. The Pacific seismic background has not changed tonight. What has changed is the context. The strongest storm on Earth is bearing down on the same geography where that background is registering. And when background seismic activity overlaps with an atmospheric extreme of this magnitude over inhabited territory, the word background stops being a reason to look away. It becomes a reason to look more carefully. While Super Typhoon Sinlaku holds the title of strongest storm on Earth at this moment, the atmosphere as a whole is not in a quiet period. The United States mainland has been dealing with its own multi-hazard pattern in recent weeks. Severe weather outbreaks moving through the Central Plains. Fire weather conditions flagged across parts of the Southwest where low humidity and high winds create conditions under which wildfires spread faster than models predict. Flood watches active in Hawaii as a separate Pacific system pushes moisture over the island chain, demonstrating that Sinlaku is not the only atmospheric event currently demanding attention in the Pacific Basin. I want to be precise about what I am and am not claiming here. I am not suggesting that the tornado outbreak in Oklahoma, the fire weather in Arizona, the flood watches in Hawaii, and the super typhoon in the Western Pacific are causally connected to each other. They are not in any direct atmospheric sense. They are geographically separate events driven by distinct weather systems operating under their own dynamics. What they share is not a physical connection. What they share is a resource connection. The resources available to respond to Super Typhoon Sinlaku, the federal emergency management personnel, the prepositioned supplies, the logistical infrastructure, the political attention of the officials who direct and fund disaster response, do not exist in an isolated reserve labeled exclusively for the Marianas. They exist inside a national emergency management system that is right now simultaneously managing multiple active events across different geographies. FEMA does not have a separate budget for each disaster that occurs independently of what else is happening. It has a total capacity that gets allocated across concurrent demands. This is the dimension of compound stress that almost never makes it into disaster coverage because it is invisible from the outside. When you watch coverage of a typhoon making landfall, you see the storm, the damage, the response. What you do not see is the conversation happening somewhere in a federal operations center about which simultaneous demands get prioritized when the available capacity does not cover all of them at once. For the Marianas, the competition is particularly consequential because supply chain and logistical challenges mean that response delays are not measured in hours the way they might be for a mainland event. They are measured in days and weeks. A day of delay in prepositioning supplies before a Category 5 makes landfall is not recoverable after the fact. The window for meaningful pre-event action is narrow and it closes fast. There is a version of this story that focuses only on the storm and the track and the intensity and the forecast rainfall. That version is important and it is being covered. There is another version that focuses only on the geology and the subduction zone and the compound interaction with the typhoon loading. That version is most of what this video has been about. But there is a third version that does not get told often enough. The version about what happens when a remote, underrepresented, logistically isolated United States territory faces an unprecedented compound event inside a national response system that is already stretched across multiple simultaneous disasters. Tonight, all three versions are true at the same time over the same islands above the same people. I want to be upfront about something before this section. There is a version of this part of the video that would be easy to make and satisfying to watch. It would go something like this. Not only is the strongest storm on Earth bearing down on United States territory while the ground beneath those islands is seismically active, but the sun itself is contributing to the instability. The heavens and the earth conspiring simultaneously over 170,000 people with nowhere to run. I'm not going to give you that version. Not because the space weather data is uninteresting, but because giving you the dramatic version when the honest version is more nuanced would be a betrayal of what this channel is supposed to do. In the window around tonight's events, the Space Weather Prediction Center reported elevated electron flux at approximately 1,000 particle flux units. Solar wind speeds were measured in the range of 500 to 650 kilometers per second. Under quiet conditions, electron flux sits well below 1,000 particle flux units, and solar wind typically runs between 350 and 450 kilometers per second. So yes, the instruments are showing readings elevated relative to the quiet time baseline. Something is happening in near-Earth space above normal background levels. But here is what it is not. It is not a major geomagnetic storm. The NOAA geomagnetic storm scale runs from G1 minor to G5 extreme. No G-scale warning of any level has been issued for the current period. The elevated readings are real, measurable departures from quiet sun conditions. But they sit well below the thresholds that produce the effects most people associate with significant space weather events. In the most operational sense, tonight's space weather is not a direct contributing factor to the compound scenario over the Marianas. The reason it is worth discussing at all is a question sitting at one of the genuinely unresolved frontiers of geophysical research. Is there any meaningful physical relationship between space weather activity and seismicity? Can elevated solar wind or elevated particle flux influence the behavior of fault systems in the crust of the Earth? The short answer as of current scientific literature is that we do not know, and the evidence for a meaningful relationship is weak. Multiple studies examining statistical relationships between geomagnetic activity and global earthquake frequency have failed to find a convincing signal above the noise. The studies that have claimed correlations have generally not survived rigorous replication attempts. The scientific community's current position leans toward skepticism about meaningful electromagnetic coupling as an earthquake trigger at the scales we are discussing. What I can tell you is where the evidence stands right now. Elevated electron flux. Slightly elevated solar wind speeds. Real departures from quiet sun baseline. Not a geomagnetic storm. Not a confirmed contributing factor to the seismic activity in the Mariana Arc. But tonight is a night with an unusual number of variables elevated above their baseline simultaneously. The atmosphere is at its most extreme expression over the Marianas. The geological system registered activity in the same window. And the space weather instruments are showing readings above quiet sun baseline at the same time. Is that coincidence meaningful? Does it represent physical coupling between systems we do not fully understand? Or is it exactly what you would find if you looked carefully at any arbitrary window of time, some collection of variables above baseline, the pattern only appearing significant because we are primed to look for it? That question is one that current science cannot answer definitively. And that honest uncertainty is more valuable to you than a confident narrative in either direction. Let me rebuild the full picture one piece at a time, because you deserve to hold all of it together before we finish. April 12th, 9:19 in the evening local time. National Weather Service time. Super Typhoon Sinlaku upgraded to Category 5, the strongest storm anywhere on Earth at this moment, tracking directly toward Guam, Saipan, Tinian, and Rota. Approximately 170,000 American citizens on those islands. No evacuation possible. Typhoon force winds inbound within hours. Seas building to 30 feet. Flash flooding imminent across all major islands. Within hours of that upgrade, a magnitude 5.0 earthquake registered near Pagan Island in the northern Mariana Islands. Depth 226 kilometers. Same volcanic island chain. Same geological arc, same window of time. The storm is not an ordinary Category 5. It intensified from a tropical depression to peak intensity in approximately 96 hours, crossing the rapid intensification threshold multiple times. It is arriving in April, an off-season anomaly enabled by a Western Pacific warm pool that has grown thicker and more energetic under conditions researchers have linked to decadal patterns of ocean heat accumulation. The storm did not stall, did not weaken, did not encounter any of the self-limiting mechanisms that reduce intensity before landfall. It is arriving intact. The earthquake is not an isolated geological event. It occurred within the Wadati-Benioff zone of the deepest subduction system on Earth, a system whose surface expression is the very volcanic island chain that the typhoon is targeting. The seismicity of that system is the seismicity of the ground under every building and shelter on Guam and Saipan. The compound interaction of these two systems, atmospheric extreme and geological activity, simultaneous, same geography, creates a risk scenario that existing emergency planning frameworks were not designed to address. Nonlinear amplification of structural damage. Rainfall saturation lowering the trigger threshold for seismically induced slope failure. coastal infrastructure undermined from above and potentially from below. Emergency response frozen by the typhoon at the exact moment any secondary geological event would require response. Supply chains already fragile, now facing compound demand. And underneath all of this, 170,000 Americans who cannot leave, served by a federal response system that has historically prioritized mainland events over territorial ones, living inside a political structure that gives them no Senate representation and no presidential vote. Here is what I want you to carry out of this video. We have built extraordinary systems for understanding the individual components of natural disasters. The track models for Sinlaku are being updated every 6 hours with some of the most sophisticated atmospheric modeling on Earth. The seismic networks monitoring the Mariana Arc are sensitive enough to detect events that humans cannot feel. The satellite technology giving us real-time imagery of the storm structure would have been considered science fiction a generation ago. What we have not built, not in emergency planning, not in building codes, not in response frameworks, not in political representation for those most at risk, is an architecture for understanding what happens when these systems interact. When the atmosphere and the geology speak to each other over the same ground in the same hours, faster than our single hazard frameworks can turn to face them. 170,000 people are about to find out whether the gap between what we know and what we have planned for is a gap they can survive. We have built systems to track storms. We have built systems to monitor earthquakes. We have built systems to measure the heat content of oceans and the solar wind from the sun and the electron flux in near-Earth space. But we have never truly tested what happens when all of those systems peak simultaneously over the same people on the same islands on the same night. Tonight is that test. And the people standing at the center of it had no choice but to stay exactly where they are.